All right, so we are now going to start some of, so this is perhaps, in simple terms, the most difficult part of complex numbers, okay? The part that students struggle with the most. Now, I'm not saying this to like demotivate you guys straight away, but that's what the reality is. Sometimes questions can be really complicated, and you know, having said that, you guys are very welcome to prove me otherwise. So first, let's talk about loci. Now, loci is something that was part of O-level math syllabus. So if there are any students who have done O-levels would know exactly what loci is. IGCSE students wouldn't. So let's just get an idea of what it means and what all we have in a loci. So it's as you can read by the definition, it's a curve or other figure formed. So it could be a curve, it could be a circle, it could be a straight line, could be an angle, it could be anything. Okay, formed by all the points satisfying a particular equation. Like for example, a circle is a loci. Okay, equation of a perpendicular bisector, as you can see, is a loci. Okay, now what exactly is it about a circle? So if you think about it, all the points on the circumference of a circle have a fixed distance from the center point. Okay, so the points on the circumference of the circle are basically locus of points. Okay, locus is a single, locus is basically a collection of points which satisfy a certain condition. And what is that condition? That condition is that they have a fixed distance, that all the points are equidistant from a fixed point. Okay, just like that, if you think about a perpendicular bisector, which is another locus that we have in our syllabus, that a perpendicular bisector is such that all points on the perpendicular bisector are equidistant from the 2 points where the perpendicular bisector is drawn. So if let's say we have a perpendicular bisector of A and B, so that means the on the perpendicular bisector, all the points will be equidistant from A and B. So whatever the distance of any point from the perpendicular bisector to point A is, it will be the same as point B. Okay. And then we have, so this is something that's completely new. We're going to learn this and we're going to learn this shortly, but circle and perpendicular bisector is something that we're all familiar with. So these are the three types of loci that we have in our syllabus, and we're going to learn them one by one. That what is the situation in which, or what's the condition where we draw a certain type of loci, and then there is shading in it as well. Sometimes you have to shade a certain, you will have to shade a certain region. How do we decide what region to shade and all of that? That's something that we're going to find out, inshallah, very soon. Okay, so let's start with a circle. So let's understand what's the condition where we have to draw a circle. Now, there are two scenarios where we draw a circle. One is when the center is origin, and then there is another scenario where the center is not the origin. It's the center is a point, something other than origin. Okay, so let's have a look at this. Now we know that the modulus of z is equals to r. Now, what exactly does this mean? Let's think about it. So if let's say z is a complex or is a variable complex number, meaning that it can vary, it can be anywhere on the plane, it's not exactly fixed. Okay. So what does that mean? Let's write that down. Where z is a variable complex number. Now, because it's a variable complex number, we're going to be using x plus yi. If it's let's say a fixed point, we're going to use a plus bi because x and y are variables, a and b are constants, which suggests that x and y suggest that they can vary. A and b, since they're constants, suggest that they are fixed. Okay. So variable complex number, and we also refer to this as a moving point. Why? Because it can be in multiple places. Okay, it can move along a certain boundary and still be satisfying a certain condition. Okay, so such that, now what is this suggesting? If z is a variable complex number, this modulus of z equals to r suggests that its distance is equal to r. Okay, so this means that such that its distance from origin, okay, so that's where we measure the distance from, is r. Okay, now imagine a simple scenario. Imagine that I tell you that on the xy plane, imagine that there is a complex number. We don't know exactly what it is, okay, but I want you to mark all the possible places where its distance from the origin is equal to r, where r can be any constant. Okay, since r is a value, it can be any number. Okay, assuming that, let's say it's 2. Okay, hypothetically speaking, let's say it's 2. So here's the origin. One possibility that the distance from the origin is 2 could be here. Okay, and then somebody else might say, well, why can't it be over here? Well, you're right, it can be over here as well. And then somebody else might say, well, it can be over here. Then somebody else might say that it can be over here. And then after we have like a whole collection of points, notice that what do we have? We basically end up forming a circle. Okay, so what does that mean? That means that if you have a locus of points which are equidistant from a fixed point, then we draw a circle. Okay, so we're going to write this down. Don't worry about it. There's a lot of information that we need to write down, but I want you guys to right now focus on understanding what the whole concept is. So if there is a complex number such that its distance from the origin is equal to r, is a fixed distance, then that is going to be a circle with center, origin, and radius r. Okay, so what does that mean? That means if you have modulus of z equals to r, this is going to be a circle with center, origin, and radius r. Okay, now within this, there is sometimes a question where you have to shade and identify where a certain type of points lie. Okay, so we're going to talk about that. So let's use a smaller version. Here it is. So this is the concept where we learn shading. Okay, where we learn the concept of shading. So if, let's say, the question is that, now first of all, let's understand what all the points on the circumference look like. Now, the condition or the one thing common about all the points on the circumference is that their distance from the origin is the same, and that's equal to r. But what if I want the points? What if I want to identify the points where all the, or I want to identify all the possible points where the distance from the origin is more than r? Okay, so in other words, if I want to, let's say, shade and identify this region where z is greater than or equal to r. Okay, what does this mean? Let's write that. Let's write it down. Greater than or equal to r. So where should I shade to identify this region? Okay, let's say we're asked to shade and identify this region, and I'm going to do this using the color blue. Okay, and let's say that not just greater, but you're also asked to shade and identify the region where all the numbers, okay, all the points. Now, when I say numbers, I mean a complex number, okay, which is a collection of 2 points, the real and imaginary. So don't get confused. So let's say we want to shade and identify the possible places where z, which is a complex number, a variable complex number, meaning that it can be in multiple places, it's not fixed, such that its distance is from the origin lesser than or equal to r. So we're going to shade this using the color yellow. Okay. Now, as I explained earlier, that from the fixed point, the distance of any point on the circumference is equal to r. So if you want to shade the region where the distance is greater than r, that means you must shade outside the circle. Okay, so the region outside represents the region where the distance of every complex number is greater than r. Similarly, if the distance is supposed to be lesser than, then once again, we will shade inside the circle. Okay, so the circle helps us determine whether we should shade outside or inside. Okay, so even if it's, let's say, greater than or equal to, you still have to draw a circle with the given radius and then shade outside. We're going to do some examples so that you guys understand. Okay, now one thing that I want you guys to keep in mind is some of you may be having this question right now, and that is that you may be wondering, what if it's just greater than? What if it's just lesser than? Okay, so let's see what we do and what we do then. So if signs are greater than or lesser than, then we draw a dotted circle. Okay, so in that case, all you have to do is draw a dotted circle. Okay, now let's do some example questions before we do the next possibility. So we're going to do some questions from the book, some very basic questions. Let's see what the deal is. So I've taken out some questions. Okay, so here they are. On separate organ diagrams, sketch these loci. Okay, first part, the loci is such that modulus of z is equal to 5, which means that we will draw a circle, we'll sketch a circle with radius 5. Okay, why is the center origin? Because inside the modulus, you just have z. When inside the modulus, you have something else, that is when we'll see that the center will not be origin. It will be some other point. So here we have a circle which will have radius 5. Now remember, it's a sketch. So this is 5, this is 5, this is 5, this is 5. Okay, we don't need to shade because it's an equal to sign. There's no shading that's required. Now part B. Part B says modulus of z is lesser than or equal to 3. Okay, so once again, we will make an xy plane, okay, real and imaginary plane, such that the radius will be, such that, and then we'll make a circle such that the radius will be 3. And the difference is that this time we will draw a dotted circle because it says lesser than. All right, remember, it's a sketch at the end of the day. So here we go. This is 3. This is 3, this is 3, this is 3, this is 3. And where are we going to shade? Because we have to shade and identify, right? We have to shade and identify the region which basically satisfy this condition. So what is that region going to be? That's going to be inside the circle. Okay, now part C. In part C, its modulus of z is greater than or equal to 4. So once again, we'll make a circle. But this time, however, we will make a solid circle. And we will once again shade inside. But we will, like I said, the circle that we will make will be a solid circle. Okay, so there you go. A circle with radius 4. That means this is 4, this is 4, this is 4, this is 4. This is minus 4, actually. Forgot to write minus in the previous question as well. But anyway, you guys get the point. Real axis, imaginary axis. It's always a good idea to label your axes. Real axis, imaginary axis, real, imaginary. Okay, now, is the center always going to be the origin? Obviously not. Sometimes the center will not be the origin. It'll be something else. So let's talk about that. What if the center is a fixed point other than the origin? So what will the equation look like? That's what's important for us to understand. So the equation will look like this. If the center is not origin, then this is what the equation is going to look like. So we will have something like this. We'll have z minus z1, which is equal to r. Okay, now what's z and what's z1? Let's talk about that. So here, z is a variable complex number. That means it can be in multiple places, and variable means it's going to be x and y, and z1 is a fixed point. Okay, z1 is a fixed point on the xy plane or on the real and imaginary plane, which means it's going to be something like this, a plus bi. Now, the question is that what does this mean, z minus z1? is equal to r. So z is a variable number and z1 is a fixed point such that, okay, such that the distance, because we're talking about modulus of z minus z1. So you can think about it as if we have AB. So if I want to calculate AB, we can do it by doing OB minus OA. So OB minus OA will give me vector AB. And then if I take the modulus, that means I'm calculating the distance or the length of vector AB. So such that the distance between Z and Z1 is R. Okay, so let's try and visualize this. Okay, let's try and visualize, and then we'll understand why this also makes a circle. So let's say this time we have a complex number Z, okay? And in fact, let's start with the fixed point Z1. So let's say that fixed point is somewhere over here. Okay, so this is a fixed point such that its real component is A and the imaginary component is B. Okay, this can be anywhere. It can be on the positive, on the axis where x and y are both real and imaginary components are both positive. It can be in any quadrant. That's what I was trying to say. Now, let's say from this fixed point, there is a complex number. We don't know what it is, meaning that it's a moving point once again. Okay, so I should add over here that this is a moving point. Moving point basically means that it can be in multiple places. This is a moving point. Okay, now from this center, from this fixed point, okay, there are points which happen to be a distance of r. Okay, so let's say r is once again 2. So that means that point could be here, that point could be here, such that this is 2 and such that this is 2. And, it could be here, could be here, could be here, 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 so many places. So many places where you can mark a point such that its distance from a fixed point is r. Now notice, what do we get as a result? Ultimately, we get a circle. Okay, now what's the difference between this circle and the circle we drew earlier? The difference is that, yes, the circle of this, the radius of the circle is r, but ultimately the difference is that the center is not the origin anymore. Okay, so yes, this distance is in fact equal to r, but the center is no more the origin. It's in fact a comma b. Okay, now what does this mean? This means that whenever you have z minus z1, where z1 is equals to a plus bi equals to r, so this is a circle with center z1, which means a plus bi, it's going to be a fixed point, and radius r. Okay, so this can also be given to you as this, z minus a plus bi. If it's not given to you like this, then make sure you first write it like this so that you can determine the center and the radius. Okay, so here the center will be a comma b and the radius will be r. Okay, now once again, let's do some questions and see what the deal here is. Okay, I just realized that before we do any question, here also we have to deal with shading. Okay, so same rules apply here as well. The rules are no different. That if let's say, let's duplicate this. Yeah. So if let's say you are supposed to, if let's say the question says that shade and identify the locus of points such that z minus z1 is greater than or equal to r. Okay, so this means greater than or equal to r. So this means that we want to identify the region where z, which is a point, okay, which could be in many places, is such that its distance from r, from the center, which is z1, is greater than or equal to r. So that means this will be, this will be outside the circle. Okay, so on the circumference, all the points have a fixed distance r. So if I want to identify the region where the distance of z from the center is greater than r, that means all such points must lie outside the circle. Similarly, if it says lesser than or equal to, that means all the points which have a distance from z1 of less than r must be somewhere inside the circle. Okay, so remember this rule, and the same rule here also applies, that if, in fact, I'll just copy paste it, we'll save some time, that if signs are greater than or lesser than, we draw a dotted circle. Yeah, here we are. Now, this right here are a few questions that we're going to solve. So let's start with the first part. So notice first part is very nicely written. You have z minus. Now after, in bracket, whatever it is after you have the minus sign is your center. Okay, so you got to make sure that after z there's a minus sign and then there's an expression. If there are, let's say, if there's an expression which is made up of two components, real and imaginary, they must be inside a bracket. If it's just imaginary or just real, then that's not a problem. But once again, there has to be a minus sign before that. So this, in the first part, notice that we have a circle, okay, but the circle will be such that its distance from the center is going to be equal to 3. That means the radius will be equal to 3. But what about the center? So in order to find out the center, you can think of it this way, that whatever it is after you have the minus sign inside the bracket, that's your center. So it's going to be 2 plus 4 iota. That means probably somewhere over here is going to be the center. And the radius is going to be 3. So it's going to look something like this. Not drawn to scale. Okay, it's a sketch. And let's position it in such a way so that the center looks like the center. Yeah, this is good. This is x, this is y. No need to shade because the points on the circumference are the points that satisfy the condition. Now part B, z minus 3 iota is equals to 4. Now before I move on to part B, I should mention that the center is 2, 4. And I'll give you a trick also, which will help you identify what the center is. So it's very similar to equation of circles that we did in P1, if you guys remember, I hope. So here's how this works. Let me write it down first. So this is A, sorry, not A. This is 2, and this is 4. So think of it this way, that you have z minus 2 plus 4 iota. So imagine that this, whatever is inside the modulus is equal to 0. And then if you make z the subject, so z would be equal to 2 plus 4 iota, and this is your center. Okay. Now in part B, you have a minus sign after z. That means whatever it is that you have after is equal to the center of the circle. Or you can also, for a second, equate it to 0, solve for z, and you will have your center in that case as well. Okay. But what are we dealing with over here? Here also we have to draw a circle, but the circle should be such that its radius is 4. And where will we find the center of the circle? The center of the circle will be at 3 iota. So remember, it's a sketch. So let's say 3 iota is somewhere over here. This is the real axis. Okay, this is the real. I've accidentally written it as x and y. Don't get confused, please. This is the imaginary axis. Okay, now, what about the radius of the circle? The radius of the circle will be 4. So that means this is what the circle will probably look like. It's going to be more above the center than it is below. And another thing is that it should have been a dotted circle. Okay, so let's fix that. Let's instead draw a dotted circle. There you go. It's a sketch at the end of the day. And the reason is less than, so that means not only is it going to be a dotted circle, in fact, we're also going to shade, and we're going to shade inside the circle. Okay, now last part C. So part C is z plus 5 is lesser than or equal to 5. So first things first, we're going to write this as z minus 5 lesser than or equal to 5. Okay. So what have I done over here? I have written it this way so that it's written in the general form, and we can see what the center is, and we can see what the radius is. So what are we dealing with? We are dealing with a circle such that its center is minus 5 and its radius is equal to what? Its radius is equal to 5. Okay, so let's draw this. So what do we have? We have something like this. It's going to be a solid circle. So if the radius is 5, then do keep one thing in mind, that this is going to be from the center. Okay, from the center, it's going to be, okay, no, actually, this is what it's going to be like. This radius is 5, so that means it's going to be tangent to the y-axis. Okay, why? Because the radius is 5. So this will be 5, this will be 5, this will be 5. And where are we supposed to shade? We're supposed to shade inside. So let's do that. There you go. Part C done. Okay, so I hope you guys are with me. I hope things are making sense. Now let's move on to the second locus, which is the perpendicular bisector. Okay, now remember, a perpendicular bisector, if you draw a perpendicular bisector of 2 points, so that on that perpendicular bisector, you have a collection of points such that its distance is equal from the 2 points where the perpendicular bisector is drawn. So any point on the perpendicular bisector will have the same distance from both points from where the perpendicular bisector is drawn, or of which the perpendicular bisector is drawn. Now, what does it look like? Let's see. So let's say you have z minus z1, which is equal to z minus z2. Okay, now here, what do we have? We have z, which is a variable complex number. Once again, it's a moving point. X plus yi, it's a moving point. And z1 and z2 are fixed points. Okay, you can call them a plus bi and p plus qi respectively. Now let's see what the deal over here is. So imagine this. Imagine that you have an xy plane here. Okay. Now on this xy plane, I want you guys to imagine that there are 2 points. Here is z1, okay, and here is z2. Now, by looking at the equation, remember, modulus means distance. Okay, modulus means distance. I want a point such that its distance from z1 and z2. Okay, z minus z1 means that its distance from z1. Z minus z2 means that its distance from z2. So I want a point, or maybe a collection of points, such that its distance from z1 and z2 are both equal. Now, one obvious point that we will have is obviously the midpoint. Okay, but is that the only point? No. So let's say this is a point over here, okay, such that its distance from z1 and z2 is equal, okay, not drawn to scale. And then you can have a point over here, and then you can have a point over here, and then a point over here, and then a point over here. Now, once you have like a whole collection of points, and then if you join the points, you will notice that what you actually have is a perpendicular bisector. Okay, so let me draw it nicely. So what you will have is actually a perpendicular bisector of z1 and z2. Okay, so not drawn to scale. Please do keep that in mind. Let's join these two as well. Let's keep them dotted. So what you see, the solid line that you see is basically the perpendicular bisector of z1 and z2. Okay. Now let's write it down. Let's formalize things by writing them down. Let's make some standard rules for ourselves. So if let's say you have z minus z1 modulus is equal to z minus z2, what does this mean? So this is a perpendicular bisector of z1, z2. Okay, why? Because you want a collection of points which is equidistant from z1 and z2. All right. Now, here also there is some shading that we must learn. So I think let's do it right now and let's get it out of the way. So here's how shading works. So imagine that you have Imagine that you have 2 points of which you have made a perpendicular bisector. So over here. Okay, so let's call this point Z1. Let's call this point Z2. So real and imaginary axis. Okay, so I'm going to duplicate this because there are 2 shadings. So we can use this once again. Now, imagine this. Imagine that you are given Z minus Z1 modulus is lesser than Z minus Z2. Now, what does this mean? This means that you want, now listen to me very carefully. You want a collection of points such that its distance from Z1 is lesser. Its distance from Z1 is lesser than its distance from Z2, okay? So you want a collection of points such that its distance from Z1 is lesser than its distance from Z2. So if I pick a point here, okay, on the side, which is on the side of the perpendicular bisector, which is closer to Z1, then its distance from Z1 will be lesser than its distance from Z2. And any point on this side, if I pick, its distance from Z1 will be lesser than its distance from Z2. Okay, now that means what is the region? If I have to shade and identify where we will find such points, what is the region that I'm going to shade? This is the region that I'm going to shade. Okay, so this region contains all the points where the distance is such that it's less than, all the points are closer to Z1 as compared to Z2. Now, what if it's the other way around? What if, let's say, this was Z minus Z1 is greater than Z minus Z2. Now you want a collection of points such that its distance from Z1 is greater than its distance from Z2. So imagine if I pick a point on this side of the perpendicular bisector, then its distance from Z1 will be greater than its distance from Z2. So Z1 greater than Z2. So where will I shade if I have to? I will shade on this side. I'll give you a simple trick. Okay, you don't have to do a lot of trial and error here, although I do encourage it, but you can use this trick and follow it if you ever get confused. Note, we always shade towards the complex number on the less than side. Okay, now what do I mean by that? So the less than side over here is, the less than sign over here is basically towards Z1. So we shade towards Z1. The less than sign over here is towards Z2. So we shade towards Z2. Okay, we shade on the side of the perpendicular bisector, which is towards Z2. Okay, so use this trick and this will help you solve nearly all your problems. Okay, now let's do some example questions related to this as well. So here I have a question from the book, and then we will do some questions from past papers as well. Okay, now let's see what this says. So it says, on an organ diagram, sketch the locus of Z minus 4i, minus 4 plus I, which is equal to modulus of Z plus 5. And now how do I know that I have to make a perpendicular bisector over here? Because towards the end, when you've done when we've done all 3 loci, then things will get confusing, okay? How do we know when to make a circle? How do we know when to make a perpendicular bisector? Well, it's very simple. Here's what you have to do. You have to, first of all, make sure that you have 2 modulus on both sides. That means we're going to make a perpendicular bisector, okay? Now, remember the rules. The rules are that you have to first rewrite it in such a way where you have Z minus Z1 equals to Z minus Z2. And, if you have to make sure that the complex number after Z is in a bracket. So if you're thinking, a lot of people make this error, that 4 plus iota is going to be the center, you're wrong, because we first have to take minus common. Okay, now or you can think of it this way, that if we have Z minus 4 plus iota, which is equal to Z plus 5 iota, so use this trick. In order to find out 1 point from where the perpendicular bisector will be drawn. Just equate this to 0 and see what happens. If you equate this to 0, you basically get z1. So z1 is equals to 4 minus iota. Okay, now do the same over here. Z plus 5 iota equals to 0. So you get z2, which is equal to minus 5 iota. So that means we will make a perpendicular bisector of these 2 points. Okay, what 2 points? Let's see. So 1 point will be minus 5 iota. That means it's going to be somewhere over here. Okay, let's try and be a little more accurate over here. Yeah. So this is 1, this is 2, this is 3, this is 4, minus 1, minus 2, minus 3, minus 4, minus 5, and minus 1. Okay, so 4 minus iota, that's going to be over here. So this is the real axis, this is the imaginary axis, and then minus 5 iota, that's going to be somewhere over here. Okay, so you don't have to join these 2 points, but you can make a dotted line to, get an idea. And the perpendicular bisector, which we're going to draw, is going to be something like this. Now, what do we have to do? We have to find the Cartesian equation of this locus. Okay, so what's the locus? The locus is the perpendicular bisector, because the perpendicular bisector is the only way that we can satisfy this condition. And what do we have to do? We have to find out the equation of this perpendicular bisector. So we follow the same rules that we do in coordinate geometry. So these are 2 points. The points are such that one point is 4, comma, minus 1. And the other point is 0, comma, minus 5. Let's make sure of that. Yeah. So first thing you want to do is you want to find out the gradient. Let's call this P. Let's call this point Q. So you want to find out the gradient of PQ. So it's going to be minus 5 minus minus 1 over 0 minus 4. So minus 5 minus minus 1 is going to be minus 4 divided by minus 4, which means that this is going to be positive 1. And the gradient of the perpendicular bisector is going to be equal to minus 1. And then we need a point through which the perpendicular bisector is going to pass. That's going to be the midpoint. So let's find out the midpoint. 4 plus 0 upon 2. Okay. And minus 1 plus minus 5 upon 2. 4 plus 0 is 4. 4 upon 2 is 2. So the midpoint has coordinates 2, comma, negative 3. Let's make sure of that. Yeah. And we also have the gradient, which is minus 1. So let's put this information together and form an equation. So y minus minus 3. Okay, we're using y minus y1 equals to mx minus x1. And let's write this nicely. Y plus 3 is equals to minus x plus 2, which means y is equals to minus x and 2 minus 3. That's minus 1. This is, as you can see, drawing it accurately sort of gives us an idea that the y-intercept is going to be somewhere on the negative side. So there you go. This is the Cartesian equation of this locus. Okay, so I hope you guys are getting the hang of it now. And what I would like to do is, I would like to, for now at least, keep it till here only. There is another locus that we are left with. So we're going to do that. But before I go, what I would like to do is I'd like to do a past paper question related to this concept. Okay, and then we will stop. And then the argument loci, we will inshallah do in the next class. So here's a past paper question. It's, I wouldn't say the easiest one there is, but here it is. Let's see what it says. So it says sketch an organ diagram showing the point representing the complex number 1 plus 2 iota on the same diagram. So the set of points representing the complex number z which satisfies so and so. Okay, so what do we do over here? First of all, now I want you to be as accurate as possible in questions like these. Okay, earlier, since I was just explaining the concept, I was not accurate. But when you're doing questions like these, even though it's saying sketch, but try and be as accurate as possible. So this is the real axis. Okay, and this is the imaginary axis. Now, first of all, the question says, sketch an organ diagram showing the point representing the complex number 1 plus 2i. So somewhere over here is 1, here's 1, here's 2. So here it is, the complex number 1 plus 2i. Okay. Now you can just mark a point, or if you want to draw a line, that's up to you. Show on the same diagram the set of points representing the complex number z which satisfy. Now, notice that we have to make a perpendicular bisector, but what do we have to make the perpendicular bisector of? So this is just modulus of z. So that means if I set it equal to 0, we have z1, which is equal to 0. That means 1 point is going to be the origin. And then if I set this equal to 0, z minus 1 minus 2 iota equals to 0. And then if I make z2 the subject, if I make z the subject, we'll have 1 plus 2 iota. So that's the second point. And notice that the question has already made us mark that. So here is Z2. Now, what do we have to do? We have to show on the same diagram, the set of points representing the complex number which satisfy the following equation. So locus is singular, loci is plural, okay? So what locus is this talking about? This is talking about a locus of points such that its distance from Z is the same as its distance from Z minus 1 minus 2 iota, okay? So such that its distance from the fixed point O is same as its distance from the fixed point 1 plus 2 iota. That means the perpendicular bisector of these 2 points. So let's draw the perpendicular bisector of these 2 points. And since we just have to sketch, you don't have to find the equation or anything. And there you go, your perpendicular bisector. Let's use a different color so it can be clearly seen. So the perpendicular bisector should be 2. Should be 1 perpendicular to the 2 points. Imagine that there's a imaginary line drawn between the two. Okay, so it should be perpendicular to that line and it should be passing through the midpoint. Okay, so this is the perpendicular bisector of Z1. And what is Z1? Z1 is 0. And Z2, which is basically 1 plus 2 iota. Okay, so 4 easy marks that you get. And it's not bad. It's pretty cool. Okay, so I hope it's clear. Now, in the next class, inshallah, we will do some more questions. Okay, I'll see if if we have to do it in a class or if I can make a video of it. Okay, but make sure that you guys understand this concept. Do whatever it is necessary to understand this concept very well. It's like I said in the beginning, it's something that challenges a lot of students. So for now, let's keep it till here only. I'll see you guys in the next video or in the next class. So take care, everyone. Allah Hafiz.